Uh, Let us proceed with our project. So, in our part 1, uh, we looked at uh, all the necessary steps. So our next step in the design workflow is to produce analysis results. Okay, so we are going to analyze our model and look at how it responds to the loading and the material properties and section properties of the structure elements that we assigned to our model. But before we do proceed, I would love us to make a few adjustments to the model. Okay, so and the first thing we are going to adjust, shall head straight to the story settings. To edit story, I want us to adjust this height, this story height for the roof. Okay, as we can see, that the height to the roof is actually 3.1 instead of 3.3. Okay, so we are going to change that to 3.1. Then also something that we misinterpreted, or something that we forgot to adjust, is the live load or imposed load reduction for the ground floor columns. Okay, as we said, this imposed load reduction applies to the columns and walls. Okay, with the purpose of optimizing design. So, given the fact that the ground floor columns do not carry or support a slab at the ground level, that is the assumption. Okay, but does not remove the fact that the same columns are actually also carrying the upper floors. Okay, so this renders this level to have the same reduction factor with the first floor level. Okay, since they are all carrying the same number of floors, so we are going to put here 15. Okay, and that is all. Then we had proposed to change the story height for the tank slab level to increase it to 2,500. And we were giving headroom reasons, but when you study the architecture drawings very well, you come to note that actually that area is not accessible, and it actually has no door to the roof level. Okay, so the roof is not accessible at all. So the story height to the tank slab of 2000 is actually sufficient. Okay, it's just to elevate the water tanks, but not for access purposes. It's just to give extra head to the water tanks so that the occupants at the topmost level receive water, okay, with enough pressure. So we shall still maintain this as of now. Okay, then don't forget to save your work. Okay, because the program can crash at any time, and you'll be forced to repeat everything. Okay, so so since we didn't adjust the height, the story height, I want us to take back the wall height for these walls. Okay, I want us to reduce them because we had assumed a story height of 2.5 and a beam depth at the tank slab level of 0.4 meter, giving us 2.1. But since we are maintaining 2 meters and a beam depth of 0.4, we shall have here 1.6. Okay, 1.6. Okay, same will apply to this and this and this. So press Ctrl, highlight them, right click and paste to replace. Okay, then I want us to shift. Okay, I want us to shift this beam from here to this point because the perimeter wall, okay, at this around this story, okay, actually comes all the way up to here. Okay, and this slab here sits on the wall, sits on that very wall. Okay, so I want us to shift this beam from this position to this position so that this beam supports the wall. Okay, the wall straight from it to this this slab here. So let's switch to plan view and read roof level. Okay, that is it. So we're going to move this beam from this point to this point. So just right click, move, then simply draw, click there, and then here, and that is it. Okay, all right. So then let us switch to first floor. The other thing I want us to adjust is the way we modeled our cantilever slabs. Okay, we modeled them as cantilever slabs, but there's these symbols. Cantilever slabs do not have beams or supports on the rest of the other three corners, on the other three edges. Okay, this signifies two-way distribution, and this one signifies one-way distribution in a way that there is a beam here and there is another beam here. Okay, which is not actually what we are trying to model. We are trying to model a cantilever slab, and Protastructure has that option. Okay, so I want us to first of all delete all the slabs one by one and we remodel them. Okay, so we are going to start with this one, delete it. So we are going to remodel the slabs, the cantilever slabs. Okay, but before we model, we need to for them they do not utilize these edge lines. Okay, they utilize points. Okay, we shall draw the slab just from point to point, from the start to the end. Then we shall specify the length and the cantilever length from the edge of the beam. Okay, then we draw the slab and position it. Okay, position it in the direction into which the cantilever faces. Okay, so I want us to draw tentative grids at the start of each slab. Okay. So I want us to draw a grid here. The start or end, but we shall start our modeling from the grid that we are going to draw. So we're going to draw that there, shall draw this. Press Ctrl to make them straight. Click, press Ctrl, click, press Ctrl. Okay, so now, so we're just going to capture the properties of this existing slab. Right click, properties. So we are going to transfer the properties of that slab to this. Okay, but before we do that, for each cantilever, I need to measure the length of the cantilever and the length of the panel or of the slab. Okay, so we are going to measure. So all our cantilevers are going to be, we shall start from there to here. So that is 1 meter. Then this slab, this panel in specific is 2450. Okay, 2450. So activate these properties. So we are going to change the type of slab here from 9. Okay, 9 means the simple supported slab. Okay, no edge beams at all. Okay, then 12 is the cantilever. So we are choosing 12. Then this is one way. Type 0 is one way. Type 1 is a two-way slab supported on all edges. Okay, with continuity on all edges. Continuity on all edges. Then 9 actually means 9 also is a two-way. Okay, 9 is also in a two-way but without continuity on any of the edges. Okay. Okay, the best way to get the explanation is by you can click on two slabs, right click, go to properties. Under here, under the slab table will be activated. Under the column type, you will have the descriptions. Okay, so 9 implies 4 edges discontinuous, but all these are two-way slabs. Okay, so 4 edges discontinuous. Two-way slab with 4 edges discontinuous. It does not mean that the slab is hanging in space. Okay. So as our type is type 12, cantilever slab, long edge supported. Okay. So let's go back. Properties. So let's choose 12 here. Okay. So once we choose 12, these 3 parameters here are activated. Okay. They are revealed. So whereby base slab is this distance which we got as 450. Then L cantilever is the cantilever length, which was 1000. Okay. Then this is an offset which is going to be populated automatically. So we are going to start modeling our cantilever. We are going to click on the start point. Okay, and any other point in the direction of the slab. Okay. Since we have already inserted the actual length, it will be captured automatically. So This is just assigning it a direction. Okay, click there. Then click the side which you want to insert your cantilever, either this way or this way. Okay, so our cantilever faces this side, so we are going to click there like that. Okay, so when you close and come back, check properties, going to see this field populated. This is simply a distance, okay, from where we clicked to the end. Okay, this distance here. Okay, so we're going to do the same to the rest of the slabs. So let's measure this. This is 250. Get rid of it. Properties. Let's just take this back to 0. Then draw from there to here. Click this side. Close there. Okay. Okay, so we are good to go. So similarly, we are doing the same to this. Delete. Measure from here to here. 1811. Okay, so let's activate this. 1811. Put here 1811. So draw from here to the nearest point where we can snap. So we can't snap here. We can only snap here. Then tap this side. Okay, so here this slab we entered the wrong length. Okay, should be 250. So that this field is also populated. 250 update like that. Okay, so let's proceed. Delete this, measure the length or the breadth, whatever, 2003. Insert it here. This is 0 by default. Then click on the starting point. Then click here. Then orient. Okay, good to go. Then finally delete this. Measure 1800. Replace this with 1800 and this with 0. Okay, draw from there to this point orient the slab. That is it. So we are done with our cantilever slabs. Okay, so we are going to generate this back to the roof level. Okay, so we are going to replace this. We are going to delete this and replace them with the other geometries, only that we shall adjust their depth to 125 and their live load to 0.4. So let's delete them. Let's delete all the slabs at this point. Right, highlight the entire model. Click delete. Press delete on your keyboard. Untick everything except slabs. and slab edge lines. Okay. Okay, let's maintain the okay, let's delete the edge lines as well and the slabs like that. So go back to first floor. Uh generate the slabs. Generate all the slabs. Okay. Generate. Tick on the slabs. Okay. Okay, let's let's select what you want to generate like that. Right click, generate to other stories, tick roof. Okay, like that. So we are now going to adjust the properties. Right click, member tables, slab table. We are maintaining the type to 12, of course. The thickness is, or the slab depth, overall depth is 125, and the live load is 0.4. Like that. Okay, so we are done. Okay, so that is it. What else do we need to adjust? I think that is all. Okay, so that is all. So we are done with our model. Okay, so now I want us to uh, go to analysis. Okay, so to carry out our structure analysis, we shall go to the analysis menu app. Okay, so we're having several forms, several options here. We're having load decomposition by finite element. We're having building analysis. We're having FE flow analysis and finite element slab pattern loading definitions. Okay, so this finite element is another form of analysis. Okay, it's another approach to analysis. So building analysis is a standard analysis whereby traditional analysis methods are used, okay, to compute the bending moment, shear force diagrams, and all the responses to the of the structure to the loading. Okay, uh, then this FE flow analysis finite element is another computational analysis method that captures more details, okay, and it's applicable to specific members. Where this mode fails, usually it is recommended to use this. Okay, so for now we are not going to use finite elements, we are going to use building analysis. Okay, so we shall head there. So under here we have several options. Okay, we have the pre-analysis where we look at the parameters, load combinations, wind story. Okay, and under parameters we have the codes, foundations. The codes, we already set our codes. Under foundations we have the allowable bearing capacity and the subgrade coefficient. So subgrade coefficient. Okay, for build for we shall look at this when we come to foundation design. Okay, then you do not want to make any changes to these two tabs. Okay, then we have the load combinations, and we are going to create automatic combinations. Okay, So to do that, I'll just click on loading generator. Okay, under here we have the option to create different combinations for steel members. Okay, we don't have any steel members right now, so let's untick that. We have two categories of combinations. There are two categories of load cases: the vertical load cases and the horizontal load cases. Okay, under vertical, we have the dead and the live. Okay, and then the pattern loads. Pattern loads are simply a combination of dead and live. Okay, pattern loads are simply uh, not a combination of the two, but these pattern loads explain something to do with the behavior or the usage pattern, the usage patterns of the slabs or the building of a given floor. Okay, so pattern loads will depict the usage patterns of a given floor. For instance, when a floor is composed of several rooms of different uh, what uses, for instance, a dining room, a bedroom, and you find that the same people are occupying those rooms but at different times. Okay, meaning the loads at the same floor keep changing with time. Okay, and this influences the behavior of the slabs themselves and the beams carrying them. That at one point there's no one in the building, or someone has shifted. If the apartment, someone has shifted and the room is empty, but the neighbor is still there. So maximum live load in the neighboring building, but minimum live load or zero. Okay, so by minimum here we mean zero. So this double dashes, okay, the equal sign here means maximum live load. Then the single dash here means zero live load or minimum, zero to be specific. Okay, so this is a loading pattern. The other pattern is the opposite of this, whereby the first span has no live load, the second span has maximum live load, and so on. So these loading patterns have effects on the structure members, for instance, columns and beams. Okay, for instance, a columns, this span of a beam will experience maximum moment, maximum bending moment. Okay, whereas this one will experience maximum hogging moment. Okay, or minimum sagging moment. Okay, depending on the length of the span. Similarly, a column stated here will experience maximum bending moment, okay, unbalanced moment in this direction. Okay, whereas a column here will experience minimum bending moment, resultant bending moment, but maximum actual load, whereas this one will experience minimum actual load. Okay, so you can choose to take all. I want us to maintain the default. Then this side, on this end, we have the safety factors for the loads. Okay, whereby with Eurocode, our maximum safety factor for the dead load is 1.35 and 1.5 for the live load. Okay, then the factor 0.7, we already looked at it as defined by annex Eurocode 0 annex A1.1. Then also I want us to create an unfactored G+2 combination, and also a factored G combination. Okay, so that is all with the vertical cases. Then when we head to horizontal cases, we have the seismic load, the notional load, the wind loading, soil pressure and temperature loading. Okay, so for this project, the project is not prone to earthquake, so that's why we didn't define the code for earthquake. That's why this option is grayed out. But the notional loading is a must. Okay, is a must to all projects. This simply caters for this is additional horizontal load that depicts or accounts for geometric imperfections. These are simply errors in construction. Okay, for instance, plumbing deficiencies, plumbing. Okay, like non-vertical walls or non-vertical structure members like columns. Okay, that induce eccentricities that in turn induce moments. They induce additional moments, okay, into our structure elements. Then we have the wind loading. Okay, so since we are buildings 7 stories, okay, I mean like G+4, then plus the roof. Okay, 6 stories. Okay, 7 actually. G+4, those are 5 plus the roof and the tank slab. Okay, so the overall height of our building is quite high, and however small the windy pressure is, okay, we can have considerable lateral displacement at the topmost part of the building, since this building, when it comes to the behavior of the wind, this building tends to act as a cantilever, and you know cantilevers deflect more at their ends. Okay, so this building will deflect more as the span increases, which in this time round is the height of the building. Okay, so we are taking this, and depending on the geometry of your building, you can as well define negative load cases. Okay, but for now, we shall not define negative load cases. Uh, we shall simply go with two cases: wind in the X and wind in the Y. Okay, and that is so. Click OK, and these are the several load combinations created. Okay, so after that, click OK. Then the other thing I want us to look at, we are going to define the wind loads. After creating the combinations and including the wind load case in the combination, we are now going to apply the wind load itself, or the wind forces at each story to our building. But before we do that, there's this section. It's for material, defining materials in our project. Okay, so this section defines the materials in our project. That is the concrete, the steel, and the reinforcements. Okay, but we shall do that later when we come to design. Right now, we shall focus more on the analysis related settings. Then here we have a unit weight of member. Now this unit weight of member, we shall switch this to 25. Okay, shall change this to 25. So go to edit materials and concrete. Okay, just click on any material like this. So we shall be using C2025. Okay, C2025. So let's change the unit weight there to 25. Why? Because Eurocode 1 provides for this value for reinforced concrete, normal reinforced concrete. Okay. Okay, so you can check Eurocode 1. Okay, under set of weights of materials. Should be at the bottom. So somewhere here. So you can see Annex A. So nominal density of construction materials. So Annex A.1, Table A.1, sorry. Construction materials, concrete and mortar. So under normal weight concrete, we have 24. Okay, but with superscripts 1 and 2. So let's see. Superscript 1 tells us increase by 1 for normal percentage of reinforcing and pre-stressing steel. Okay, so the 24 applies when the concrete is not reinforced, but when you reinforce it, you're increasing it by 1. So we have 25. Okay, so that's why we use 25. Then we can also go ahead and explore the values for the other materials like mortar, cement mortar, lime mortar, and so on. Okay, so click OK and OK. Then unit weight of blocks. These are now the max span blocks or the filler blocks in between our ribs, in our rib slab. So the default value is 4.5. However, for this value depends on the kind of blocks and the specifications or the weight of the blocks you're using. Okay, so let's first close here and go to settings, slab settings, and see that you can adjust this value from here under slab settings, the design tab of slab settings. So the parameter is ribbed slab filler block unit weight. So this is the unit weight of these max span blocks in kilonewtons per cubic meter. Okay, so let's see which value we are meant to get. Okay, so according to the supplier specifications, let's visit internet. So one of our known suppliers is Uganda Clays. So the blocks look this is how they look like when laid on the slab. Okay, this is how they are arranged. Okay, and then we are interested in the specification. So this is a single unit or a single piece. Okay, and this supplier called Uganda Clays supplies various sizes from 4 inches thick to 12 inches thick. So we are designing for the most common size, which is 6 inches, okay, whose dimensions are 300 millimeters by 300 millimeters by 150, which is the 6-inch. Okay, so 300 by 300 by the thickness of 6 inches or 150 millimeters. And the supplier goes ahead and tells us that in each square meter of your slab, you will find yourself with eight of these. Okay, so these 8 only apply when you're having this block spaced at a center to center spacing of 150 in the direction perpendicular to the ribs. Okay, meaning the such ribs are 150 millimeter wide. That's when you'll have eight pieces. Okay, then the weight or the mass of each unit is 8.5 kilograms. So if each unit weighs this volume, I mean if each unit has this volume and weighs 8.5 kilograms, how about a cubic meter? Okay, so how many units are in a cubic? So you are going to get 1 cubic divided by this volume. What do we get? So the volume is 0.3 times 0.3 times 0.15. So we're having a volume of a single piece occupies 0.0135 cubic meters. So how many are there in a cubic? 1 divided by 0.0135. So we're having 74.0741. So roughly 74.1 pieces are in a cubic. But one piece weighs 85 kgs. How about this 74? So times 8.5. So a cubic weighs 629.6 kilograms. In other words, this is the density. This is the density of these blocks, 629.6 kilograms per cubic. But now we are converting the program needs the input in kilonewtons. So we are converting this value to kilonewton. Okay. How are we doing that? We are just we are gonna do it in steps by first converting it to newtons. Okay, so you multiply it by the acceleration due to gravity, 9.81, and then you divide by 1,000 to convert to kilonewton. So we have 6.18. Okay, so you round off to 2, you have 6.18. Then this is what we are inputting, 6.18 kilonewtons per cubic. And see that it's way above the 4.5, which is the default value. So which has a significant impact on the loading. Okay, so that is it. So that simply affects the self weight of the slabs. Okay, it affects the self weight of the slabs. This value here. And so that when you take it back to 4.5, the self weight here reduces to 2.85 kilonewtons per square meter of slab, 2.85. But when you go back and put 6.18 and check again, can check in any panel you want. The self weight increases to 3.018. Okay, Okay, so now all loads are captured. You can now go all the gravity loads are captured. We can now apply the wind loading. Okay, so let's go back to analysis, building analysis, wind and story load. So click there. So under here, we have this table. Will populate or get or this table will show the various story loads and wind loads, okay, applied to our building. You can see that it captures both the notional loads and the wind loads. Okay, in other words, the lateral loads. So right now, so far, we do all values are 0. Okay, all values are 0. So I guess with the notional loads, the values will be populated after analysis. Then with the wind loads, the values are going to be populated immediately after calculating our loads. So these loads act as the center of mass of our building. Okay. So here we have the total mass on each floor in tons, and the center, the coordinates, the coordinates of the center of mass for each story or for each floor. Okay. So now to calculate and apply the wind loading, you just simply click on the wind load calculator here. Okay. So we have options here. I have the parameters, we have the wind load in the x direction and the wind load in the y direction. So we have default values. These are the default values which you may just simply apply, and we do not want to do that because I want us to make adjustments to those values before we apply them. So if you want to apply them to the building without making any adjustments, simply come here and click apply. Okay, so now let's go back to parameters. So we have the base wind parameters. Okay, so I have the base wind speed, or rather the fundamental base wind speed. Okay, and then this value, so this is the speed you read from the wind map of your country. Okay, this is speed, 10-minute gusset wind speed. Okay, used for structural design purposes. So yeah, depending on the location of your site. Okay, this wind speed is the speeds are computed by the weather stations or the meteorological centers. Okay, of the locations where the site is situated. So for Kampala or for our site location, we are going to use a value of 18.1. So we are going to maintain this. Okay, so this is a fundamental base wind speed. Then these factors, we have the direction factors and season factors, which you multiply with the fundamental base wind speed to get the base wind speed. Okay, so you can visit Eurocode 1 part 4 for clear definitions of those terminologies. Okay, but all you need to know is that the wind force applied to a building, both the wind force and the wind pressures the wind pressures eh, that that apply to the claddings and the wind force that is applied at the centers of mass, the center of mass or the center of inertia, they are affected by several factors. Okay, like the season factor, as I said, the terrain category, the orography, that is how hilly the site is or the site neighborhood, okay, or the area of influence. Okay, so we do not look only around the site, but we have to consider the area of influence of the wind. Okay, which is usually a huge area covering like a full village. So you need uh, to consider the topography of the entire uh, village, sort of. Okay, and you need to have these parameters: the horizontal distance of the site from the top of the crest. Okay, actual length of the downward slope in the wind direction, LOD, and the actual length of the upwind slope in the wind direction, LOU. Okay, alright, so for now, I want us to leave these values default. Okay, I want us to maintain the default values for this. For the terrain category, we have categories from 0 to 4, whereby category 0 is for sites at the coast or the sea. Okay, so ours does not apply. Category 1 is for flat areas with negligible vegetation and without obstacles. Okay, but far from sea. Okay, alright, so like deserts, desert areas, so savanna areas, savanna vegetation, sort of. Then category 2, areas with low vegetation, side grass, and necessary obstacles with separations of at least. Okay, so our side does not belong to any of these three. In category 3 is areas with regular cover of vegetation or buildings. Okay, so you can look at this illustration to relate with your site. Okay, this looks so a suburban area. Okay, or with isolated obstacle with separations of maximum 20 obstacle heights. Okay, then category 4 is area in which at least 15% of the surface is covered with buildings. So for our site, we are going with category 3. As category 4 is for built up city areas. Okay, so we are going with category 3, since this applies to our site. Okay, then you can choose your building category: reinforced concrete, steel concrete, and so for more detailed calculations, you can consult Eurocode 4. Eurocode 1 part 4. Okay, Eurocode 1 4, this one. Okay, yeah, you can see for instance expression 4.1 gives us the best wind velocity VB, which is product of this direction factor and the season factor plus the fundamental base key wind velocity VB 0. Okay, which I talked about, the value read from your wind map. Okay, there are also other definitions or expressions related to the same, but our target in this is to be able to calculate the wind force on at its height. Okay, that is at each story. Why we consider story levels is because the stories have what we call rigid diaphragms, or diaphragms that transfer the wind loads. Okay, so the slabs are rigid in that horizontal direction. They are stiff enough to actually take up or absorb all the wind, okay, from the cladding, so from the walls. So the wind is received by the walls or the claddings, but is taken up by the slabs because they are stiffer in that direction. But these slabs are not stiff in the out of plane. In the vertical direction, they are not stiff. So they transfer the loads to the more stiff members. Okay, for instance, shear walls in that direction. In the vertical direction, the shear walls are stiffer. So these slabs will transfer these wind loads to the shear walls, which in turn transfer them to the foundations. In case you don't have shear walls, then the only option left is the beams and columns themselves, the frame itself. Okay, so the frame itself will take up those loads. It will transfer those loads to the foundations. Okay, for a non-reinforced concrete frame, like a steel frame, then you'll have to use either bracing or shear walls. In case you don't have shear walls, then you have to design bracings to take up the wind loading. Okay, so after filling all these parameters, uh, you can check out for the values. Okay, check for the values of the pressures and the loads. Okay, so this is the load at that story due to wind in the x direction. Okay, so the load at story 1, and then the load, as I said, this acts at the center of mass or center of inertia of the story. Okay, so this load, the load of 6.5, load of 14 at story 2, 16.1 at story 3, okay, and so on. Then similarly, in the y direction, also have these values. Okay, so to apply these loads to the building, simply click apply. Or if you want to create and save a report, you can click there. Okay, so this is our report, which we can export to Word, and so make edits, for instance, in the headers and also in the write-up. Okay, so simply click apply. So on applying, our loads are applied. So when you expand here, our 6.5 value is here, the x, and 8.2 is here in the y. Okay, these are simply coordinates where the forces are. These are coordinates of the centers of mass. Okay, all right. So Same applies to story 2, story 3, and so on. So when you're done with that, click OK. Okay, so we are done with the load. So all loads are applied to the building. So our next step is analysis. Okay, so to carry out our analysis, we shall go to the analysis tab. Okay, we shall later come back and also look at the rest of the tabs like mode options, post analysis, and so on. Okay, so for now, let's stick to the analysis tab. So we're having options here: building analysis and design. Shall skip this for now. Then you also have column and stock wall design, beam reinforcement design, steel member check, design check. Sorry. Okay, so in case you want to uh, carry out the building analysis and also column or member design immediately without checking the analysis results, you tick these as well. Okay. If you want to only focus on the analysis, then later carry out the design, you only tick the building analysis option and click start. Okay, so we are done with the analysis, which has taken 3.12 seconds. Okay, so from that you click OK. Alright. So after that, you can now check. Can go to post analysis and check for check the analysis model from here. You can also carry out design from here. Okay, if you want. You can as well also check the analysis model using this button. Okay, so for now, let's click here. You can also generate an analysis report. So this is our analysis model. Okay, this is our analysis model, and as you know, it's made up of line elements. The horizontal line elements are beams, and the vertical line elements are the columns. Okay, so the slabs are not shown at the moment, but we shall work out that. Okay, we shall work it out later. Okay, so under here, we have 3 tabs. The general tab. Okay, so simply for maneuvering our model. Okay, can switch to 2D. From there, can toggle off 2D. Can go back to 3D. Right click to rotate. Right click and rotate. Okay. Okay, you can filter out stories, you can filter out access, and so on. Okay. Under elements, you can decide, you can choose to not show nodes, support, loads, and so on. But the most important tab is the results tab, where we have our displacements and the forces. Okay, under displacements, you can toggle them on and look at the deflected shape of our model. 3D deflected shape. The one in red, the one in blue is the original position of the members. Then red is a deflected shape of the entire building due to change in position of the joints or the nodes. Okay, can click this animation. You can run the animation to see how the building behaves under different load cases and load combinations. So the default view is due to the dead load case. You can click on live load and see how the building deflects. Okay, you can try wind in the X, and also focus on X values. See how it deflects. Okay, this is wind in the X. See, then when you rotate it this way and turn on wind in the Y, you can see how it deflects sideways in the Y direction. Okay, you can display frame views. For instance, you may just be okay. You can also, before you go to frames, let's display our diagrams. You can, the default load is the actual load. The default force, the actual load. So let's switch the combinations. Let's switch the factored G and F combination. So you can see that we have big values of actual load as we descend the building. Okay, so at the bottom most end of the columns we have bigger actual loads. You can also look at a graphical representation of the actual loads. Okay, so you can also display the torsional moments. Okay, torsional moments. Okay, so from there you can V2 is shear force in beams. Okay, shear force distribution in beams. Let's switch to factored load combination. See, you can turn off the labels from here. Okay, so V2 is shear force in the beams. M3 is bending moment in the beams. Okay, then V3 is shear force in the columns. Then finally M2 bending moment in columns. Okay, so as I said, you can also filter out and display only. So let's go to filters down here. So you can choose to not display any story like that. You can choose to only display story 1. Okay. But for me, I want to display all the stories, but only a given grid or a frame. So you can turn off all axes and choose a story, axis 1. Because this entire frame consisting of all stories, but along axis 1. Only members along axis 1 or grid 1. Okay, let's try grid 5. Okay, so this is grid 5. So you can turn on displacements. Okay, you can look at the displacement in the x direction. Okay, you can see. So I have a maximum value of 26 and a minimum of 3 millimeters. Can turn on labels from here. Okay, so back to diagrams. Okay, so back to diagrams. So can display the actual load. Switch to the factored load combination with a label. So these are the actual loads in columns. Consider that this is our maximum of actual load of 876.7. So this is a most heavy loaded column. Okay. Basically because of the long spans on each side. Okay, then the torsion, then shear and beams can increase the scale, can also reduce it. Okay, so this is shear distribution in the beams. Okay, then this is bending in beams. Consider for the column supporting the tank, the beams since the span is short, these beams are spanning shorter distances. The bending in those beams is hogging. Okay, so there's no sagging in the beams due to the longer spans on the either end. Okay, so the beams tend to hog, meaning the tension, the topmost fibers of the beams are experiencing tension, whereas the bottom fibers get to experience compression. Now, so we cannot lap our top steel within this span, as it will be on a weak area. So we cannot lap our top reinforcement from this span. Okay. Then we also have shear in columns V3 and also bending in columns M2. Okay, so that is it. So you can take when you're making your reports, you can take screenshots can capture screenshots of this, okay, and put them in your reports. All right, so that is it. That is it with the analysis. Okay, so as we said, we need to make a few adjustments in analysis settings so that the slabs are also displayed here in the analytical model. So we are going to close. Okay, so go back to analysis. I mean, go back to model options. So go to model options, come to slab model, and tick, simply tick include slabs in building model. Okay, then also include columns in finite element model. Okay, but this one does not apply as of now, so let's leave include slabs in building model. Then you ensure that those slabs are meshed, so you tick all stories. Okay, tick all stories so that the loads are captured well. Then this applies to solid slabs, and with the waffle slab, with the ribbed slabs, we are going to, the default option was do not include in building model, but we are also including them in the analytical model. Include slabs as beams in the building model. So that is it. After there, just simply go back to analysis and analyze again. So ensure you tick building analysis and then start. So we get a warning, actual load comparison warning. Okay, so this warning, this tells the difference between building analysis and decomposed beam loads is 40%. Okay, so this is an error in the transfer of loads from the slabs to the beams. As you can get details from the actual load comparison report here. So click there. Okay, so as you can see, we have warnings difference between, so the same warning that was displayed. Okay, so this is the table. We have two tables. We have the dead load and live load table. The dead load table, each table will display the loads at each story and the total load. So this is the total dead load from the slabs. It's the total live load from the slabs. Okay. Then we also have loads decomposed to the beams. This is a table. Is loads decomposed to the beams. Okay. Then we have the building analysis loads. So these are the finite element loads. This is the finite element load decomposition, as you can see, FE. Then the building analysis loads. You can see the total dead load 7592 and the total live load 477. So meaning the building analysis did not capture all the loads. So instead of capturing 798, it captured 477. Okay. All right. That is with the live loads. Then with the dead load, we're having a bigger value here compared to the 7586. Okay. So to sort this, we're going back to want to close this. We go back to model options, a slab model, and untick use decomposed slab loads. So we are unticking this. We do not want any finite element decomposition approach. Okay, we are just interested in viewing the slabs in our model. Okay, so untick that, go back to analysis, tick, and reanalyze. So our analysis is done. It took 4.32 seconds. Okay, so click OK, go back to post analysis, or simply click close there and tap here to go to post analysis, the analytical model. Okay, so that is it. You can now see that our slabs and ribs are displayed. Okay, you can see these are our cantilevers displayed. These are our ribs. This is the tank slab at the top. Okay, you can now toggle on your displacements and the animation. Okay, so you can clearly see that all members are interconnected and they move as a whole. Okay, so the entire model deflects or gets displaced as a whole, which means the columns and slabs and beams are well connected. Okay, in case your model has connection related issues, you'll see some members over deflecting compared to the rest of the members, and they can easily be noticed. So once you see such, it means you have to go back to that specific element or member and put it right. Okay, so this animation can also enable us so the animation will also enable us to tell whether our model our modeling was done well. Okay, so you can see that the displacement due to wind in the x direction is more pronounced at the topmost nodes. Okay, so we have a bigger lateral displacement at the top compared to the bottom. That's why it is crucial to check uh, to apply wind loads to tall structures compared to low-rise structures. Okay, so that is it. So we are done with analysis. Yeah, so in our next video, we are going to look at design, whereby we shall check each and every member we have modeled and tell whether the section properties and material properties we assign to them are sufficient to take up the bending moments, the shear forces, and all the forces that we have obtained in our analysis. Okay, so design will be all about that, checking the initially defined sections, adjusting those sections, providing the required reinforcements, okay, reducing the sections where necessary, which that may not apply here because we have all the sections we assigned are minimum, so we shall have to just increase the section properties where we have failures, Okay, we shall also reorient our columns in case certain dimensions become longer than the default dimensions and tend to compromise the architecture spaces. Okay, so we shall reorient our columns, okay, and position them in the best way possible, both with respect to the moments and also the architecture space. So we shall be weighing between architecture space and structure capacity of the columns. Okay, so we are done with that. All right, so allow me end here, and I would love to thank you for your time. Thanks for watching, and endure to check the channel for another tutorial or for our next tutorial. Okay, so we shall design all the structural elements, and we shall also design the staircase, by the way. Yeah, we shall design the staircase, but we shall design it in 2D. So we shall use a different program to quickly design it in 2D so that we do not leave it out when we are preparing our construction drawings, okay, which do not only serve as construction drawings but also serve as blueprints which we submit to the authorities for building permit acquisition and for approval purposes. Okay, so we shall also prepare a structure analysis, a structure design report, which we shall attach to the drawings and submit together. Okay, today